go on. We have another talk before the break. Kwabena. Kwabena Bediako from Berkeley. Thank you for joining us and for braving the cold weather on the East Coast here.
Yeah. Thanks a lot.
Yeah, please go ahead.
Yeah, thanks, JP. Thanks for the invitation. I think I'm glad that I was actually able to make it this year, and it's been fantastic. And I'm looking forward to the rest of today as well as the workshop on Friday. Oh, that's true. The thing is, it hides the. There you go. All right, we're almost. All right. It's weird how you can't see the mouse when we're trying to get rid of that panel at the top, but hopefully it might. All right, I think we're good now. Okay, thanks, Shiki. All right, so what I'd like to talk to you about today are, as you can see from the title, superlattice structures in intercalation compounds. And what I'll try to do is to walk through a few case studies of some materials that myself and others have been interested in and studying, and give you, I guess, a few I think key points that I think are relevant to both the local sort of single ion anisotropy and magnetic exchange effects, as well as longer range effects of disorder in this family of materials, and things that we're starting to learn ourselves about these systems. And there'll be examples drawn from a subset of this very diverse family of materials. So to begin with, it's probably helpful just to get everybody on the same page. What do we mean by, let me see, a superlattice, of course, I think everybody would know this, but we can have some atomic lattice, and that atomic lattice is going to give us, we could sort of model its electronic band structure in some way, and then if we create a superlattice, so we have some modulation of that atomic lattice, and that might be due to some structural distortion, like the classic Peierls distortion, or it might be because we introduce some other chemical species. These might be atoms, ions, molecules, and such that are arranged in on top of this atomic lattice in some longer range, with some longer range periodicity than the original structure. And in that case, then you're going to get effects that Leslie talked about and others did yesterday, associated with band folding effects, right? And one case that has sort of been of intense interest recently is are the superlattices that form from moire sort of structures, right? And I'll talk a little bit about that at the workshop on Friday. But today I want to talk about sort of the second case where perhaps what is introduced into the system is some other chemical species, right? And so those not only will sort of create this band folding and other effects, but it might be possible to introduce, in this case, what we'll talk about, magnetic behaviors from paramagnetic centers. And so the class of materials we're going to be thinking about are these transition metal dichalcogenides that are intercalated with transition metal ions. And when we look at these transition metal dichalcogenides, so you have some transition metal ion. Usually this is a second or third row transition metal ion in the host lattice, so in the parent sort of TMD, and then you have these orange or yellow spheres. Those are the chalcogens, typically sulfur or selenium, but they're also tellurium analogs as well for these intercalation compounds. But the interlayer region between these TMD layers can allow you or creates interstitial sites that are either octahedrally, I can't see the red very well, I'm a little bit colorblind, so I can't even see where I'm pointing, but creates octahedral sites where you could have some ion in between the layers, as well as tetrahedral sites. And over here, what I'm showing on the left and on the right are the 1T and 2H structures of the TMD, right? So in both cases, you can have octahedral and tetrahedral sites. By far the most common intercalation compounds of TMDs have this 2H structure. There are a few based on this 1T structure for the zirconium and hafnium dichalcogenides. And by and large, when you intercalate transition metal ions, or when you grow crystals that have transition metal ions intercalated, more on that point later, in these materials, they will sit in the octahedral sites in pretty much all cases, with the exception of with some of these 1T system TMDs, where you can get a mixture of 1T of the octahedral and tetrahedral occupancies. And in part, that can be understood simply by looking at the geometry, the size of those octahedral and tetrahedral sites. So if you compare, say that the size of, let's say you think of like selenium-based ligand field or crystal field octahedral site, you'll see that in the zirconium case, for example, or even in this case across the row, or for all the metals, the size of that that interstitial region is comparable to the size of the octahedral sites in sort of bulk iron chalcogenide compounds. Not so for the tetrahedral sites, which are generally much smaller than what you find in, say, iron selenide, but in the zirconium and hafnium cases, well, the zirconium case, you have sort of the highest, the largest tetrahedral site. And so it turns out that zirconium iron intercalated zirconium selenide does give you some about 20 or 30% occupancy of the tetrahedral site. But by and large, the intercalation goes into the octahedral site. That's the main point, with the exception of a few others. Okay, and so this then can give rise to a whole, myriad of materials, and this is just a small, what is really a small subset of some of these structures. In principle, there's an infinite composition space, because you can change, yes, the host lattice, whether it's niobium or tantalum or zirconium or hafnium and so on, sulfur and selenium, you can change the chalcogen, and then you can change nearly continuously the stoichiometry of the intercalate, right? And so we're going to talk about compositional disorder a little bit later on, but here what I'm showing are sort of the stoichiometric compounds, are a few of them actually, just a few of them, and what has been reported about their magnetic properties. So for example, the vanadium intercalated niobium system is a candidate alter magnet. The chromium in 1/3, niobium and tantalum sulfides have been known since the 80s, 70s or 80s to be chiral Heli magnets, at least the 80s, by groups in Japan, Togawa's group and others. My group has recently published, at least put on archive, a paper about the chromium 1/4, which is a 120-degree non-collinear AFM. I'll tell you a little bit about that today. And then, this is Ephraim's material. This cobalt 1/4 tantalum selenide is also another candidate alter magnet, and so on and so on. So there's tons of stuff that you can do here. And so what's really interesting about these materials is just sort of the playground that they afford for looking at the various effects, right, that can be tuned to give rise to different kinds of magnetic orders, with this kind of model where we can think of the magnetic exchange and interplay with anisotropy, the Lashinsky-Maria interactions, which, as I'll talk to you a little bit more, give rise to canting of spins. It can basically promote orthogonal alignments of spins versus parallel and anti-parallel. And so as you tune the periodicity or symmetry, as I'll talk about disorder, you're able to play around with all these different terms and how they interact with each other, which one dominates, and so on. And so that gives you a really large playground. And so we're going to walk through a few cases of these and just look at a subset of these interactions, try to understand them to some level, and then see if that gives us any guidelines, any basic principles for designing materials within this space. So what I hope to accomplish today is to provide just a little basic guideline for understanding the energetics of this intercalation, sort of from a chemical perspective, just a couple slides on that. What can intercalate into what, right? How should we think of these? Why is it that niobium and tantalum are the dominant host lattices for this and not, say, molybdenum disulfide or tungsten disulfide, which might be interesting if that could work. And then we'll go into sort of the effects of single ion anisotropy, the local ligand field around that intercalated ion. How does that affect magnetocrystalline anisotropy, right? Looking at a couple of cases. And then, what we've been learning in my group about the magnetic exchange in this family of materials, they're metals, and so it's presumed that the interactions between the moments would be what's known as RKKY, but it turns out that in many cases, if you actually try to interrogate that, it turns out not to fit that model. And so why is that? And then we'll explore a couple of cases where you get non-collinear interactions, so not sort of parallel antiparallel, but maybe they're either canting, right, within the plane in these helimagnetic cases, or this 120-degree FM, arising from either the non-centrous symmetry of the crystal lattice, and so then the Gialis-Maria interaction, or even if we have a centrosymmetric structure, you can get non-collinear magnetism from geometric frustration. So we'll talk about that. And then finally, and what I really want to share with you are sort of some things that we're starting to understand about superlattice disorder, okay, in these materials. So that's maybe a lot, but my hope is just to give you an overview of some of these topics, and I erred on the side of trying to cover all of these things to some level instead of going in. So we'll see if that's a good idea or not. Okay, so sometimes when I talk to people about these materials, they will say, "Oh, yeah, okay, that's great. What, can you do this? Can you put iron into molybdenum disulfide, right, or something?" And that would be great because it's magnetic and it's also a semiconductor or optoelectronically interesting. Then there could be cool things that we might be able to do with that. And so what I wanted to start with is to ask, why do these transition metal ions intercalate into, or when you grow crystals? Because we use the word intercalation. I'm going to talk a little about synthesis. But why do these compounds form, right, in the first place? And so one way of thinking about that, which is purely based on thinking about the energetics of charge transfer, does not really consider the fact that you're making new covalent bonds when these transition metals are in between the layers in that way, but simply based on charge transfer, it gets you sort of going, gives you a start, is to think of, well, what is the electron affinity of that host lattice? Because when these intercalation compounds form, we can, to a first order, understand why they would form simply based on charge transfer. The transition metal ion that is going into the interlayer space is going to give up some electrons to the host lattice. And so if that host lattice's preference for accepting electrons is more favorable than the energy it takes to give up the electron from the transition metal, then great. If not, then it's probably not going to work. So we can just look at the electron affinity and for the niobium and tantalum alkygenides, the orbital parentage of the band crossing the Fermi level is predominantly dz squared, at least at gamma, and it hybridizes with other orbitals, but it's predominantly dz squared. Sort of for a very crude sort of estimate, we could think of that as the dz squared band, and it's partially filled, so that tantalum and niobium alkygenides and selenides, sulfides and selenides are all metals. And so the question is, well, how much does this want an electron versus how much does the transition metal ion that we want to react with it want to give up, right? And so it turns out that because first row transition metals by and large have, you know, work functions, let's say greater than 4, between 4 to 6, you really need large electron affinities, host lattices, to get that reaction to happen. This is very different from, say, the intercalation of a lithium ion, right? You know, like in battery chemistry, or even a rare earth. Those are very, very electropositive, and so they are very readily, you know, giving up electrons, and so you can intercalate lithium into, say, MOS2, or MOTE2, or MOSE2. Those have, you know, small electron affinities, but if you want to put a transition metal ion into a host lattice, you'll probably need to think about some of these ones down here with the larger electron affinities. And so that at least is a place to start, you know, to think about, you know, and so in my group, we've tried, maybe somebody will find a way to do it. We've tried to put some of these transition metal ions into, you know, molybdenum and tungsten, into the group 6 chalcogenides. Never work, right? But with zirconium and hafnium and these other ones, it actually does. And we're sort of trying to work on these 10 cases as well. Yes?
What's your threshold?
Oh, like where it stops working?
Yeah.
For us, you know, below molybdenum sulfide doesn't work so far. But I mean, I don't know exactly, you know, what that precise threshold is. Now, again, this model is only considering that charge transfer, but you're making a covalent bond between the transition metal and so, for example, Leslie here has shown that like palladium, right, can do interesting reactions with tellurides, right? And you'd say, well, but molybdenum telluride or tungsten telluride, they have very, very small electron affinities, but if that palladium, which is sort of, if you think of it like hard, soft, acid-base chemistry, if that palladium is like a soft, right, thing, and then tellurium is soft, then maybe the covalent interaction can promote some interesting chemistry. So this is purely sort of thinking electrostatically about it. But in general, for these transition metals, you know, we're stuck to the group 4 and group 5 chalcogenides so far. Okay. And so thinking about synthesis, you know, I've used the term sort of intercalation, and they are intercalation compounds because there's a host lattice and then there are these intercalants. But most of the time when these crystals, myself and others, when we grow these crystals, we grow them as we would any other bulk 3-dimensional material. It's not as if we sort of create the host lattice first and then necessarily perform some other intercalation, though that's what I'm showing in the bottom here. But most of the time, these crystals are grown as, you know, or these materials are synthesized as bulk crystals by chemical vapor transport, right? And so I'm sure one of you know, talking about synthesis here in this school, maybe CVT has been one of the topics, and so I don't want to go too much into that, but the general idea is you can have either the elemental precursors sort of on one side of a sealed ampule with some transport agent that volatilizes them, and then they crystallize on the other side. And the energetics of the formation of that volatile product and the formation of the final material, that's going to determine whether you end up growing at, say, at the hotter end or the colder end, right? Whether the reaction is endothermic or exothermic is going to determine that. And this is a you know, very common actually purification method, right, for metals in industry. Yes.
So I'm just wondering about the intercalation.
The second one?
Do you think the electron affinity view of being able to intercalate different resistant metals will be different for whether you try to do a CVT growth with all the constituents, or if you make the dichalcogenide and try to intercalate some soft chemistry or something?
I think the thermodynamics are the same. I think whether there's interesting opportunities to sort of play around with what you could kinetically isolate. So there might be opportunities to isolate things that are metastable by the second route, right? Where you use some soft chemistry, which is some of the stuff that we've looked at a little bit, to intercalate, versus growing at 1,000 degrees or 900 degrees, where you're probably going to. So as an example of that, I mentioned that predominantly the intercalation compounds are all the 2H structure. And so if you try to grow, let's say, iron intercalated or chromium intercalated tantalum sulfide under conditions where if there was no intercalant, you would end up with a 1T phase, which has the CDW. If you try to do the CVT, at least for us and the other, you always end up with a 2H phase, right? It just goes to that. But we're writing this up, but you can do the chemistry with the soft chemistry with a 1T. And you end up with the magnetic material that also has the CDW. And it's a bit of a, structurally it's a bit of a mess, but it's there, right? And so, and one question is, okay, well, how do those things play off of each other? At least they appear to coexist within the resolution of, the probes that we've used so far, so 5 nanometers of an electron beam, you can see both. Whether that means, whether there's more granularity that we're not picking up, difficult to say. But you're absolutely right. That I think that's where the opportunities are. Or playing games like twisting, right, and other things, and then doing the soft chemistry. Those are all ways that you can access structures that you might not be able to get at high temperatures. Okay. And so what I wanted to do today was just, focusing mostly on the bulk systems, but go through just a few case studies that I think are really are interesting, at least to me, that help us to understand something perhaps about these different interactions and how the interplay, right, among them. So these are the, I guess, 4 systems we'll talk about today. And so the first thing I want to think about is single ion anisotropy and how that impacts unquenched orbital angular momentum and what that means in terms of magnetocrystalline anisotropy and the magnetic properties. So if we have some transition metal intercalated TMD, as I said, most of the, in nearly all cases except for the group 4, like the zirconium and hafnium cases, the intercalant is going into the octahedral interstitial site. And it's going to, we can think of it sort of starting out with the transition metal atom as if the transition metal then transfers electrons to that host lattice. So it's going to end up being usually divalent or trivalent. Divalent for, say, iron and cobalt, trivalent for vanadium and chromium. So from a sort of very local coordination geometry type of picture, a very, chemistry-centric or inorganic chemistry-centric picture, would think of how that charge transfer is, leading to some additional carriers going into the host lattice. We'll see what that means for the band structure in a little bit. And then the intercalant goes into these octahedral sites. And if you have a perfect octahedral coordination geometry, then what that's going to do is it will take your 5d orbitals and it'll split them. And group theory gives you this result. It will split them into a triply degenerate and a doubly degenerate set, a T2G and an EG set. But then in these materials, there's an additional trigonal distortion, right? So you take that perfect octahedron and you stretch it basically along the crystallographic C-axis of the material, and that is going to, decrease the symmetry around that intercalant ion, taking it to D3D instead of octahedral. And what that does then is it's going to split the T2G yet again, and get, you end up with sort of the model you could think of is that the dxy and dx squared minus y squared are the lowest lying orbitals, and then you have the dz squared next, and then the dxz and yz are the highest. And so what that means then is that for transition metal ions like iron and chromium that have different numbers of d orbitals, you end up with very, very different extents of quenching of that orbital angular momentum. So orbital angular momentum, when you have just a free ion, or you have all the d orbitals being degenerate, you could think of the electrons as being able to hop between all the orbitals, right? Because they're all at the same energy, and so you get whatever the maximum orbital angular momentum you might expect for that electron count, for that d electron count. But once you start to split them, now say for iron, you still have a large amount of orbital angle. You have L equals 2 because this there are 3 electrons in this x squared minus y squared pair, and so you could think of it as one of those electrons can hop right between those two, and that gives you some unquenched orbital angular momentum. It's not fully suppressed. But then for chromium, whereas for a free ion you would still have a non-zero L, now for chromium, which is D3, you've sort of filled these the xy and the x squared minus y squared. Well, you've half filled them, and so you can't have sort of electrons sort of hopping between these two orbitals, and so then you have L is equal to 0. Basically, you can say +2 -2. They will cancel out, and so now in this case you have quenched orbital angular momentum, and that's going to have a significant impact then on the magnetic properties of the extended solid, and we see that play out and we'll look at just a couple of examples. We see that play out in iron intercalated tantalum disulfide and iron intercalated niobium disulfide, where for the tantalum case, these are ferromagnets, and they have an easy axis ferromagnetism. So the moments are oriented along the crystallographic C-axis, and you have very, very large, these are extremely hard permanent magnets. They have a very, very sort of large anisotropy between the field being oriented along the C-axis and in the plane. Okay, and for the niobium case, they're still also oriented along, the moments are oriented along the C-axis. It's just, it turns out that you have antiferromagnetic interactions, and so you end up with an AFM. But contrast that with the chromium analog of this system, the chromium, say, tantalum sulfide, or the chromium niobium sulfide, chromium 1/3 niobium sulfide, where going back one, where you have quenched orbital angular momentum, and so that ends up giving rise, in this case, to easy plane magnetism. The moments are oriented within the plane, and there's a more very interesting sort of effect associated with the broken inversion symmetry, which I'll talk about later, which leads to a chiral helimagnetic structure. But the main point for this particular comparison is the effect of orbital angular momentum, unquenched orbital angular momentum in the iron case, promoting the spins orienting along the C-axis, versus in the chromium case where it's quenched, they are sort of in the AB plane. Okay, and so that's sort of the effect of that local ligand field splitting. Let's move on to thinking about how these magnetic ions can interact and talk to each other, right? And the first thing we need to recognize is that when we have these intercalation compounds, we can have a practically infinite composition space that, of how much of the intercalant is there with respect to the host lattice. But at specific stoichiometries of intercalant to host lattice, you can have ideal commensurate superlattice structures that form. And so for a 1:4 ratio of the intercalant to the host lattice, so this is the 0.25 or 1/4 intercalation, or a 1:3, so the 0.33, you can construct respectively a centrosymmetric superlattice that has a 2x2 superlattice structure. So the new unit cell is twice the size of the original TMD unit cell, or a square root of 3 by square root of 3 superlattice structure. Okay, so these are the two commensurate superlattice structures, and as I will try to impress on you later on, historically we've always sort of assumed that if we made the composition 0.25 or the composition 0.33, that we had pretty much exclusively the 2x2 or the √3 by √3 superlattices, right, respectively. It turns out that this is not at all the case, and I'll explain a little bit more why. But these are the commensurate intercalant superlattice structures, And so to understand how the symmetry of these superlattices can affect the magnetism, I want us to consider the chiral helimagnets, which are these chromium 1/3, tantalum, and niobium disulfides. So we'll look at the chromium 1/3 niobium disulfide and the chromium 1/3 tantalum disulfide and compare their magnetic structures, their phase diagram, and what we've learned about these systems. So in these systems, you have with the 1/3 stoichiometry, you have this square root of 3 by square root of 3 superlattice, which is non-centrosymmetric. And so that then allows you, so going back, did I have it? Sorry, I should have copied it here. But that allows you to have a non-zero Dzieloszynski-Moria term, right? Which that term relies on broken inversion symmetry. And that promotes, because it's the cross product here, that promotes or drives the system towards an orthogonal orientation of spins. And that the combination of that with the magnetic exchange is going to lead to canting of the moments, okay, in the material. And so what you have, so here is the Dzieloszynski-Moria interaction, which promotes orthogonal spin orientations. What you have when you combine the fact that this material has low magnetocrystalline anisotropy because it's L equals 0, right? So it's this easy plane, right, system, and now you have this DM interaction. What you have in these materials is that in the plane, the moments are all ferromagnetically coupled to each other, but then as you move along the crystallographic z-axis, each sort of stack or each layer of these spins is canted a little bit with respect to the one below it, so that you end up with a helimagnetic structure, which you see on the right. And then as you apply a magnetic field within the plane of that crystal, you can start to unwind this helimagnet into these chiral soliton lattices until at some critical field you end up with basically a forced ferromagnetic state where all the moments you've sort of you've overridden that sort of the sort of DM interaction, and you've forced everything to be aligned with the magnetic field. Okay, so this is a pretty interesting class of materials that was, I think, some of the first reports were from Miyadai in 1983, or maybe even there was some work before that. But conventionally, it is assumed, because these materials at large, you know, the intercalated TMDs are metals, that the is that right? Oh, when did we start?
We started late, so
okay. All right, how much time?
Maybe 10 minutes.
Whew, okay. All right. So the assumption is that the model for magnetic exchange is RKKY, which is sort of a model that says, all right, I have local moments, right, local magnetic moments, and these are coupled together. They talk to each other through some itinerant electrons, you know, in some conduction band. And so what that means then is that the magnitude of the magnetic exchange J is going to depend on the Fermi wave vector, basically in effect, sort of the carrier density, if you will, right? Or more accurately, the Fermi wave vector. And so and the distance between the ions, so that you have this oscillatory, oscillation between positive and negative J's that gives rise to whether ferromagnetic or antiferromagnetic interactions. So when we look at the niobium, the chromium intercalate niobium and tantalum disulfides, we can ask the question, why, these have qualitatively very, very similar phase diagrams, but the ordering temperature for the tantalum analog is higher by a shade than that of the niobium, but otherwise they are really similar. And so we can use these two systems to compare and try to see what do we learn about the magnetic exchange here. And we can also learn something about the D term in these materials, because for the niobium analog, the wavelength of that helimagnetic winding is about 50 nanometers, and it's half that in the tantalum. Okay, so the tantalum analog seems to have a much stronger Dzieloszynski-Moria interaction, as we might expect. But how does that compete with magnetic exchange. That's what we want. Okay, so we want to learn something about the electronic band structure, because then we can model that RKKY term, because we can get the Fermi wave vector, so we can do ARPES, where we get information about the band structure by looking at how a photon kicks out an electron right from the material. And so what do we know, first of all, about the host lattice? Well, if we look at 2H-NBS2 versus 2H-TAS2, we know that there is more dispersion, there's greater dispersion of the bands in the tantalum analog, right? That's what you can kind of see. I'm trying to find my, yeah, there it is. That's what you can kind of see over here, and also on the right. And this is because the tantalum d orbitals are larger. Its valence d orbitals are larger than those of niobium, and so you have and also energetically there's a better match with sulfur, and so you end up with better overlap, right, between the orbitals of the tantalum and those of the sulfur, and that overlap is what is dictating the spread of the bands, right, in your electronic band structure, as sort of Leslie was showing with the model, the sort of Hoffman type model, type binding. Okay, and so what we can do then is we can look at the niobium and the tantalum analogs. We can measure their electronic band structures and extract some information about the Fermi wave vector. And what you find is that indeed, even in the intercalation compound, the tantalum analog is more dispersive. It has a larger hole pocket, and in fact, it is the size of that, or the magnitude of that Fermi wave vector is exactly opposite what you would expect, considering that the tantalum analog has a higher ordering temperature. If you model that RKKY interaction, you would actually predict that there should be weaker magnetic exchange in tantalum than in niobium, and that is opposite of what you observe, right, with the tantalum analog having the higher magnetic ordering temperature. And so this starts to suggest that maybe we shouldn't just assume that RKKY is the most dominant or the operative magnetic exchange interaction. And in fact, that kind of makes sense, because if you follow that up with some calculations, you find that there is extensive hybridization between the intercalant and the host lattice atoms. And RKKY relies on sort of these localized moments connected to these itinerant electrons, and really sort of assuming that the host lattice, its bands are rigid and not influenced, not being influenced, fundamentally by that magnetic dopant ion. Okay, whereas here we have extensive hybridization, which is perhaps in the end not too surprising, between the chromium and the intercalant. And so indeed, we can then ask, well, why is the ordering for tantalum ordering temperature higher? Well, it turns out that it is the increased overlap. So we should probably think more about a super exchange type interaction, which has to do with how the ligands, the tantalum, sulfur, chromium interactions, and the nature of that orbital overlap. That increased overlap is what gives rise to the higher ordering temperatures, and not simply the sort of the band size of that Fermi wave vector. And if it was that, then if it was basically the RKKY, then we could start thinking of ways to use doping as a way of tuning the magnetic interaction, right, and the magnetic ground state. But if it's this, then we have to maybe think instead about strain, right, and how, right. So these are important in terms of how we play around with what's going on in these materials. And then why does the Cara-Heli why is it shorter for the wavelength of the helimagnetic winding for tantalum? Well, the J, the magnetic exchange, has gone up only a little bit, right, between niobium and tantalum, but D goes with the spin orbit coupling, which goes as basically Z to the fourth, the atomic number to the fourth. So that D term has increased a lot more in going from niobium to tantalum than J has, and so it is able to outcompete and tighten the winding of these systems. Okay, so then one slide on non-collinear magnetism in another system. Now this is the chromium 1/4 tantalum sulfide. Now you still have this triangular lattice, but you don't have broken inversion symmetry, and so you don't have this GM interaction. But another way you can engineer non-collinear magnetism is by geometric frustration. So in this case, you have antiferromagnetic interactions between the chromiums. And on this triangular lattice, as you might know, there is no way, if they are sort of aligned out of the plane, to satisfy antiferromagnetic interactions in all three. And so instead, what this system does is that you have a canting of the spins, right, or a rotation of those spins in the plane, so that you form a 120-degree AFN in this material. And so this, I think, is the first in this family of materials to have a non-collinear sort of ground state. Okay, so in 5 minutes, I want to talk about what I really want to talk about, which is disorder. So traditionally, when we think of disorder in this family of materials, we think of compositional disorder. So for example, Emilia Morrison did some really beautiful work looking at different stoichiometries of, say, the intercalation and intercalant ions in the host lattice, right? And showing how that changes so much, right, about the magnetic properties of these materials. And we also have known for a long time that for a particular composition, if you grow the crystals and you cool them at vastly different rates, right, like you quench cool versus slow cool, as is the case in many systems, you end up with very, very different types of size of magnetic domains, right? And so this sort of composition and structure disorder is well established. What we found quite surprising when we're looking at that helimagnetic system that I talked about is we had 2 batches of crystals, well, not just 2, there were more than 2, but 2 sets of growths, one which we call slow cooling, about 20 degrees per hour, and the other which we call fast cooling, which is about 60 degrees per hour. And what we found is that these compositionally, stoichiometrically, they were identical within our ability to resolve that by elemental analysis. But they showed, and this is a Lorentz TM, so it's an electron microscopy image where we are sensitive to the magnetic texture of the material. We're basically imaging that helimagnetic winding. So these stripes that you see, the horizontal stripes, actually the more dominant sort of bands that you see that are curving and waving, those are just associated with the lamellum of the fib cutout of the material. But what you want to pay attention are the horizontal stripes, which are actually a little bit fainter, but you can see that they're tighter on the right versus on the left, right? And I could show you images and so on and all of this, but what I want to draw your attention to is the fact that when, for the left where we have these, for the same material, in this case the niobium, you can have, a critical field where it goes to the forced ferromagnetic phase of, let's say 30 millitesla, or on the right for the same composition, that could be, 200 millitesla. So this got us thinking, what on earth is going on in these systems? And we used some atomic resolution methods and started learning about, how vacancies, small amounts of vacancies, how, different growth conditions can affect how these vacancies cluster or are distributed. And that just got us starting to think about how might we want to model and think microscopically about the structure, and I'll skip through what that means for the DM interaction. How do we want to think about the structure of these materials? And so I go back to this picture, this model of these commensurate intercalation superlattices. If you grow 0.33 or if you grow 0.25, is it a given that you have even mostly the 2 by 2 or and the root 3 by 3? We thought so. But with some theoretical collaborators, we started looking, so we looked at the zinc and the scandium intercalated compounds because what we're most interested in is the structural, sort of the configurations of these intercalants and not their magnetic behaviors. And the DFT gets a little bit complicated if you have paramagnetic ions because it's doing a 0 Kelvin, unless you use some other methods, I guess, a 0 Kelvin model or computation. And so we just wanted basically diamagnetic transition metal ions to use to model a divalent on the zinc to model, say, iron or cobalt, and scandium to model, say, a vanadium or chromium. Okay, And what we found, and to cut the chase, is that if you have the, if you're targeting the 0.25 stoichiometry, there is a very, very small window or regime, and so you have temperature versus the stoichiometry. This stoichiometry, by the way, is for the for a bilayer. So what you know, this it's basically half or so the value you expect for the bulk. Okay, it's for a bilayer model. But it turns out there's a very, very small window where you will expect the 2x2 to be the long range 2x2 to be the low energy configuration. So if you're growing at 800, 900, or 1,000, depending on how you cool down, you might trap the system in a mixture of 2x2 and root 3x3. And the reason for that is that at high temperatures in a 0.25 stoichiometry, entropy favors a disordered root 3x3 because it's a configurational thing, right? There's lots of ways to arrange a stoichiometry of 0.25 in a root 3x3 structure because there are lots of vacancies. And so entropy favors this, and then as you're cooling, the hypothesis or the idea was that you'll start to nucleate the 2x2 domains, and you can then end up trapping root 3x3 domains between these 2x2s. So that's what the theory says. So let's see in an experiment. So we had made this material, the non-collinear AFM. By X-ray diffraction, it was a well-ordered 2x2. We saw no evidence in X-ray diffraction of any root 3x3 in any of the frames. We go frame by frame. All the superlattices we see are 2x2. When we look in the Raman, we see the 2x2, the modes, the phonon modes associated with the 2x2. And we see some other modes that look eerily similar to sort of what you might expect for the root 3x3, but other people have assigned those to out-of-plane versus in-plane vibrations. Okay, so then we go and do 4D STEM, which is a scanning electron diffraction experiment. I won't go into too much of the details here, but what we can do is we can, because the cameras for electron diffraction are generally much more sensitive and have a wider range of I guess dynamic range you could say of than X-ray detectors, we can pick out that we not only have 2x2, which is the very the dominant, the bright superlattice pattern, but we actually do have some root 3x3 in there. And when we do the 4D STEM experiment and we scan to try to figure out where in space are these, we see these regions, the green domains are the 2x2, and then the dark regions are where there is no 2x2. And if you then use the electron beam from the 3x3 reflection to form the image, that's where you see, right? So you have this, this is precisely what we were expecting to see over here, right? And so the key is that, what this starts to tell us is that, you can have these mixtures, and in fact, and that leads to an anomalous Hall effect in this chromium 1/4 tantalum system that we should not expect to see based on the symmetry of that non-collinear AFM. It should exclude an anomalous Hall effect, but we see it because of some extrinsic effect associated with these basically AFM domain walls. Okay, so the main take home here is that you can have these superlattice structures that are not what you expect simply because of how one grows it, but that could be a frustration, or it could also be a tool for us to use to design a wider array of these materials. For example, in some preliminary work, what we've shown is that if we grow these compositions at the 1/4 and we deliberately quench them, we get Raman features that are exclusively root 3x3 because we are trapping it. We're trapping it out on the right? And then you take that and you start to anneal it slowly, you can get the 2x2 structure. So that is just an important consideration because that can lead to extrinsic effects in the measurements. Okay, so I'll leave this up at the end. I hope we've gone through some of the interesting possibilities for looking, for tuning the interactions in these materials. I hope you've learned something new, and I'm happy to answer any questions if there are. Thank you.
Great, yes.
Nice job.
Bediako. So, is there any reason to study only this? Mostly, I saw that sulfides. I mean, like previous other groups are in. Why prefer sulfides over the other chalcopenides?
Instead of selenites?
Yeah, selenites, dendrites.
Oh, I think there's lots of reasons to study all of them. Why, in our case, at least what we've published so far is only on the sulfides, but there's been a lot of work also on the selenides. This is one example from Efrain's group on the cobalt-1,4 tantalum selenide. I think there's a niobium analog as well. And this nickel system is pretty interesting. It goes between superconductivity and ferromagnetism, depending on the amount of nickel. So I think the selenides are very interesting as well. I think in general, you find that the selenides might have a slightly higher ordering temperature than the sulfides. Again, this might be related to the idea of orbital overlap being stronger in the selenides. That's not always the case, but there are some cases where that's true. I think the issue maybe with the tellurides can be this: is it energetically favorable to form the compound for the reasons I talked about? So I don't think there are too many examples of the tellurides, but I think you might be able to get something if you went to the group 4 tellurides, the zirconium and hafnium, because there with the transition metal, you're starting out with a much larger electron affinity, so you might be able to get some mileage there. But I'm not sure if I've understood your question, but yes, I've only talked about sulfides today, but the selenides and tellurides are very interesting, yes.
Thank you. Yep.
Two questions. So you showed an image, the DM image of the slow cooling versus fast cooling. And
Yeah.
Speak a little louder so everybody can hear you.
How the distribution of the defect was.
Yeah.
I guess like you were studying the distribution of defect by looking at the images, like how do you, question one is like how we able to, or how does one do that sort of analysis? The second question is, so this order, or like what kind of defect could there be? Could that be understood in terms of like electron affinity, or is it
The defects?
Yeah, or is it a very simple?
So for first question, I think your question is how can one probe, or maybe a little bit more detail on this, essentially. So yeah, so here you have two samples compared, where the stoichiometry is, as far as one can tell, identical. Give or take, whatever the limit, the error of uncertainty limit is in, say, an EDS or some other elemental analysis, right? And yet, magnetic behaviors are very different. And then if one gets does this cross-sectional analysis, and I'm not showing all the data here, but a subset of it. This crystal, as far as one can tell, over multiple fields of view and with TM, if you're doing atomic resolution, you're looking at small, but you can kind of grab a few pieces, right? You see the intercalants when you look along this zone axis. This particular zone axis is the zone axis that will allow you to see this root 3 by root 3 ordering nicely. Here, you see, they seem to be there always, right? But on the right, you get these, for the right sample, you get regions where it appears as though there's a gap. There's some vacancy, or at least it's not ordered in that region. And so, the way we think about this, because how else can we rationalize? If we take as a given that the compositions are effectively the same or identical, the way we think of it is that this one, the DM interactions are weak, because even though you have the same, on average, number of vacancies throughout the entire crystal, when you cool slowly, you're smearing out those vacancies throughout the whole crystal, right? And so then you're uniformly weakening the DM interaction everywhere, right? Leading to this sort of softer ferromagnetism. On the one on the right, when it's cooled a little bit faster, you end up, for the reasons later on that we understood, like this configurational disorder thing, you end up clustering your defects in some regions. so that everywhere else is sort of full strength DM, and then there are regions that have no local DM. And so if I showed you the Lorentz TM, we can show as we apply the field, how do these textures that I'm showing here, how do they wind and unwind? And you can actually see them pinning and unpinning at defect sites. It's actually pretty cool. But whereas this one is very smooth. It's continuous, it's smooth. Whereas these, you see these pinning and unpinning, and I can show you that later if you're interested. And so that's the picture that we had. And that, but then motivated us to try to understand a little bit more about the disorder question. And then your second one was basically, I get, so that model is just considering like the nearest neighbor interactions. It's a Monte Carlo model using some parameters obtained from DFT, which is just considering the nearest neighbor interactions. And it's a relatively simple model, but it works really nicely to sort of predict what we actually end up seeing in an experiment. I don't know if that answers. I know that was a question.
Have you done any attempts to just instead of slow cooling through, where you expect the 2x2 phase to form, estimating what temperature you expect that to be stable, and just quickly dropping from your synthesis temperature to that temperature, and then letting it kneel there for?
Yeah, we've done so. Yeah, we spent the fall doing experiments like that. It works. So it certainly is very easy if you have a stoichiometry of the 0.25, and say you go to crystal, and it looks like it has some mostly 2x2 by Raman spectroscopy. You can heat it up back to the growth temperature and quench it, and you get a perfect root 3 by root 3 signal from Raman. You can then take that and, as you're saying, sort of start to back off on it and cool it, and it starts to convert back. We have also done some experiments, I think, which is what you're asking, where, okay, after growth, you rapidly cool down and then leave it sitting there. That seems to be also, that seems to be probably like the way to go. That seems to give you, as far as we can tell so far, there's still more to be done, the best quality of some of these crystals. But there are some other things that we still don't understand that sort of show up. Like sometimes you get very, very broad modes, yet still when you do that. And so it seems much, much easier to get a root 3 by root 3 structure with the 0.25 in our hands at least than it is, right, to get the 2x2. But yes, that is precisely, I think, what one would need to do and try to understand how to use that sort of post-synthetic thermal treatment to really, obtain a long-range 2x2. And I think of it almost as like a crystallization problem. But now the crystallization is of the intercalants, right, in the interlayer. And so I actually think that what you probably want to start with is you want to find a way, because normally when you're cooling down from high temperature, by the time it becomes energetically favorable to form the 2x2, because the enthalpy crosses over the entropic, you're at the highest temperature, and so you're at a high temperature, and so you nucleate the 2x2 domains really fast. And then they might end up bumping, crashing into and creating domain walls that you don't want between slightly offset 2x2s. So instead, probably what you want to do is what you're saying is you rapidly go down here where you have a root 3 by root 3, and then you warm up to that sweet spot for the 2x2 and allow those nucleated domains, which are hopefully far apart from each other because there are very few, to slowly grow out so that you minimize. So that's sort of that's what I think is the guiding principle maybe for this, but we'll see. And it will depend a lot on the intercalant too. I think there's some intercalants where that's easier to get to work than others.
There's one more question.
No, I
Good. Okay, I'll ask the last question. We can discuss this later. If you have you thought about just putting in multiple species, like just trying to get the, you talked about configuration entropy, getting that to dominate somehow such that, I don't know, if you sort of control the iron, let's say, if that's the species you want as 2x2,
there's a
Not in the right stoichiometry.
there's a paper. Leslie, were you on this? I think there might have been a paper. I think Leslie was on this paper. I was involved. Where I think they introduced lithium, right? I don't know if that was anyway. I think it was Hugh and G's, maybe. But anyway, I think Leslie was involved in it, where they introduced lithium and sort of pushed it into a different structure, and maybe sort of the lithium sits in some sites and sort of so I think that is a way of doing it. I had a student who really wanted to, or have a student who really wants to just throw different metals in. Let's do nickel and cobalt and iron, like all of them. And I've sort of been holding them back, and the student made the mistake of listening to me, so they haven't yet done that experiment. But I think that that could be a really interesting, I mean, teasing out what's going on might be a nightmare, and so that's my hesitation. But I think the one way is by introducing sort of these very dissimilar metals like a lithium, and I think exactly that's probably going to nudge the intercalants around, because I think they can actually move really. We see them moving in the TM sometimes, so you have to be careful. Like those atomic resolution images were under very, very low dose, very, very challenging conditions, but then you can get it. If you just do it with the brute force, regular, you're going to just, which maybe you could use to pattern the intercalation, but that's a different. Okay.
Okay, all right, we better stop, so thank you. So we're running late, so let's say we're going to start again at 11:05, which is about 15 minutes. Okay, so get some coffee.